Okay, good. So I would like to tell you that Professor Klaus Mainzer is a German philosopher and scientist. He is author of the well-known book, Thinking in Complexity. He gave guest lectures on or carried out visiting professorships in many countries of the world, and also presented online lectures here at the Academy of Sciences of Moldova. He is a theoretician in the field of complex systems and artificial intelligence. And today he will present the lecture on artificial intelligence, which is of great interest nowadays. So Professor Klaus Mainzer, please, you have the floor.
Thank you very much, Mr. President. Esteemed colleagues, excellencies, ladies and gentlemen, thank you very much for this kind invitation to your academy. It's my honor today to give this invited lecture to your academy, and congratulations to your National Day of Independence today. The topic of my lecture is, as you already mentioned, artificial intelligence, present status and future prospects. And that is actually on the background, you mentioned it in your introduction, of a long-term research engagement of mine, which was documented here by these recent books. For example, here the second edition of the book Artificial Intelligence, When Do Machines Take Over? Or Limits of AI from 2022, or Quantum Computer and AI, and recently in this year a book on neuromorphic computing. That is a kind of computing which is more brain oriented. So on this background, I will start with some remarks concerning digital computing and AI, the origins, then modern machine learning, and then I will consider important paradigm shifts in technology, namely to more brain-oriented computing, the neuromorphic computing and quantum computing, and I will finish with the future challenges of hybrid AI, which integrate all these different approaches. Now, let's start from digital computing to AI. And here we first look at this famous colleague, Alan Turing, the British computer pioneer, who for the first time in 1937 introduced a theoretical concept of a digital computer, the famous Turing machine. The Turing machine is a complete theoretical concept, and that is very easy to understand. Here on the left, the strict separation between memory and processor. The memory is illustrated here in the case of Turing with a tape, and the tape is divided into squares, and the squares can be printed or deleted by symbols, the digits, in this case, the simplest case, namely the numbers 0 and 1, which are our bits today. And you know, any kind of information can be encoded by bits. And then, besides the memory, the second important part, the processor. And that is here in yellow. The processor contains the instructions and computational devices to manipulate the digits. And then later on, it turned out that several suggestions, definitions for digital algorithms are mathematically equivalent with the Turing machine. And therefore, the Turing machine, following the so-called Church thesis, is until today the representative concept of a digital computer. Turing also came up in that time with the concept of a universal Turing machine, and a universal Turing machine that seems to be a little bit philosophical, but it is very practical. It means it is a machine which can simulate all kinds of other Turing machines. And nowadays, every technical digital computer is such a universal computer. It is a general purpose computer. It does not only run one program, but several programs, as we all know from our laptops. Now, that is also called the von Neumann architecture, because John von Neumann in the 50s came up with the technical realization of these Turing machines in the so-called John von Neumann computer. And until today, we call these architectures the John von Neumann architecture in our smartphones, in our laptops, in our super computers. Now, on that basis, in 1950, also Turing came up with his first definition of what artificial intelligence means. And that is the so-called Turing test. And the Turing test from 1950 only requests, it's a kind of simulation game. It only requests that a machine, a computer, should be called intelligent if in its reactions and its answers, it cannot be distinguished from a human by a human interrogator communicating with both computer and the machine. And in the beginning of the 50s, people tried to simulate at first logical thinking, because they thought, oh, logics, that is in the center of human intelligence. And actually, in the beginning, there were some nice programs which simulate logical deduction. You know, these if-then rules. If this and that is the case, then it follows that and that. And so that was a simulation of mathematical or logical proving. And that theoretical concept, some years later, was for the first time applied to the so-called expert systems. And the idea was an expert, for example, a physician or an engineer, has some typical expert knowledge. And this expert knowledge must be brought on the machine to the expert system, represented in if-then rules. For example, here in medicine, if this and that infection time is the case, then this or that medical indication must follow. And in that way, the idea was, if you find some concrete symptoms of a disease, for example, an infection, then the system is automatically be able to deduce the general disease, which is the case in this for this patient. And in the first, it was rather successful, but later on there were limitations. And the same can be observed here in robotics, or here in the first period of robotics, symbolic AI, a robot need a complete representation of the environment and all his actions. That is illustrated here in this cartoon. And if the robot is changing its position, then it must be documented in these formal instructions. But obviously, humans animals do not need symbolic computer programs and symbolic updating situation. They interact bodily by sensor signals with their environment. So that was a first restriction and limitation of this approach in AI, which is historically called symbolic AI. Symbolic because it is oriented to symbolic or formal logic. And the same is true, by the way, for the expert systems, which I mentioned before. Before a human expert is not only distinguished by textbook knowledge, which is represented in if-then rules, an engineer or a physician, but these people have a big background knowledge, which is mainly unconscious and documented perhaps in many, many data. And the same is true, by the way, for pattern recognition. If you recognize a pattern, a photo of a person, this photo consists of millions of pixels, and it makes absolutely no sense to have logical rules to manipulate each of these pixels. And the single pixel is absolutely non-interesting, because in order to have an idea to recognize the picture, we need the mass of data and the statistical distribution of data. And therefore, since the 80s, roundabout of the last century, there was a paradigm shift in AI from symbolic AI to a more statistical orientation, and statistical machine learning now became the fundamental basis for this new kind of AI approach. And that is nowadays called machine learning. And all our breakthroughs nowadays, you can read every day in the newspapers, they are based on machine learning. And that is subsymbolic AI, subsymbolic because it is no longer oriented to symbolic or formal logic, but to statistics. And later on, we will consider some combination of these different approaches in AI. Now, let us consider in more detail machine learning. What does that mean? Now, very easy. You all know statistics, and in statistics, we start with a finite sample of data. And in this case here, these are these finitely many pairs of inputs and outputs. For example, input may be the input of a medicament to a patient, and Y, the output, may be the reaction of that patient here. And now you have a finite sample, and your system is trained with these samples. Now, in order to get a general mathematical framework, in order to get more insights later on and advices, you assume that these data here are generated by an unknown random experiment. And the random experiment is mathematically represented by random variables. Random variables are here the big letters, X for the input, Y for the output. And then you consider in statistics the joint distribution of these random variables. And from this general expression, you can infer, you can derive properties such as, for example, the probabilistic expectation of the output if some input is given. On the background of our example here in medicine, there is now a patient who gets a medicament, and now the probability of the reaction of this patient on the basis of your trained sample, or a binary classifier assigning each XX input to a class that is more likely, and that means you train the system for binary pattern recognition. Now, how can we compute? How can we compute this target pattern to recognize a certain pattern, classification, and so on? That is nowadays done by the so-called neural networks. The neural networks, here are some simple examples, are simplified computational models of the human brain. And you know, the human brain consists of neurons. Here in the graph, they are represented by nodes. And these nodes are connected by arrows in the graph, and the arrows represent the synaptic interaction between the neurons. And here in the graph, these arrows are weighted by numbers, and the numbers represent the synaptic intensity of the signals. And then such a neuron is said to be excited or to fire if the sum of the neighbored inputs here, of the neighbored cells, is larger than a certain threshold value. And by that, you get a sequence of signals which are led through the architecture here of the neural networks. That means a data stream. And the data stream is triggered by learning algorithms. And the learning algorithms, we can distinguish several kinds. For example, supervised learning. Supervised learning means that at first the system is trained by some sample. For example, by a pattern of a figure, of a photo. A photo means, as I already mentioned, a distribution of many, many pixels. And that the training can be realized by adjusting the weights to your neural network. And then the system spontaneously is able to recognize these trained photo among a huge number of other pictures. And that is used by police, for example, hunting criminal persons by their photographs since many years. Non-supervised learning means that your system is spontaneously able to detect similarities between data. And according to this criteria, the system is spontaneously able to classify these mass of data. Reinforcement learning means that the system is able to improve its solving solution, its solving strategy by rewards from outside. And deep learning only relates to the depth of the neural network, and the depth means here the number of layers. This is a technical, simple example with only 4 layers. The human brain, by the way, the neocortex of the human brain has 5 layers. And very similar to the human brain here in the neural network, at the first layer, only colored pixels are distinguished. The next layer, they are connected as edges and corners, and then as partial faces, and finally, the whole faces are recognized. And that's all. That is modern machine learning. Modern machine learning means nothing else than pattern recognition in a mass of data, big data, by learning our algorithms. And there are amazing examples nowadays of application. For example, in science, in physics. Perhaps you remember in 2018, there was an announcement by CERN. You know this famous research center near to Geneva. And they announced that the Higgs particle, a famous crucial particle in elementary particle physics, is now detected not by human physicists, but by machine learning, by artificial intelligence. Now, actually, that is an example of pattern recognition, of supervised learning. Supervised learning, because at first there was a human, namely Higgs, the Nobel Prize winner later on, who predicted, who deduced from the premises of the standard model of elementary particle physics the existence of such a particle. So theoretically, there must be such a particle. And he also predicted that this particle decays in several other particles. So what he predicted is a pattern of particles. So to say, the fingerprint. Police would say that is the fingerprint for the existence of this particle. And now you must imagine in the Large Hadron Collider that is illustrated here, there are permanent collisions of protons, and these protons generate billions, not millions, but billions of data. And now, supervised learning, the system was trained by our fingerprint for the Higgs particle, and then it was able, among the huge number of these other data, which are represented here by these blue triangles, so to say, the background events, the signals of our pattern, the fingerprint, namely of the Higgs particle. Supervised learning for elementary particle physics. And now the same technology is used in medicine. Breast cancer. At first, supervised learning, the system is trained by criteria of cancer. And then it is able, here it is illustrated on the left, it is able to distinguish the distribution of the cancer cells here in red from the distribution here in green of the healthy lymph nodes. Or here in 2018, Google came up with AlphaFold. AlphaFold is a multi-layered neural network which discovers fitting shapes and folds of proteins from sequences of amino acids. Here is such a proton sequence represented by the amino acids as building blocks. They are represented here by these letters. And in this way, malformation of structures, for example, the very early emergence of cancer tumors can be discovered, and by that, causes of diseases. Now, this is the example since last year, the chatbots, and with the chatbots, AI has arrived in our everyday life. Everyone is now confronted and can be in interaction with AI. The chatbots are, as you perhaps know, are programs which are able to reproduce any kind of texts. That may be articles in the newspaper, that may be articles in scientific journals, as last as they are text-based, that may be even examinations at the university, written examinations by the students, at least in the, let me say, behavioral sciences, social sciences, and humanities. And therefore, some people are horrified by that. But I can only say, don't worry. From a mathematical point of view, let's have a look to the machine room of these chatbots. And there we find the already mentioned two well-known learning algorithms. First, supervised learning. Supervised learning, as I explained, only means that the system is trained at first by a lot of documents. And then reinforcement learning means that the system, in this case, by communication with the user, is able to improve its answers by the rewards from outside. Of course, that is in general no absolute optimization. and sometimes they are running into that paths. But anyway, it is very realistic to communication, former times between humans here with the chatbot. But we must not forget that is only statistical calculation. This machinery does nothing else than computing expectation values of possible data. And therefore, I sometimes call them stochastic or statistic parrots. And, you know, and I hope I could explain it to you. The problem is not the algorithm. The problem is not the AI. The problem is not the mathematics here. The problem is the interaction of these systems with humans, with the media, with politics. And that is illustrated here. Perhaps you could recognize her with the former Chancellor of Germany here in interaction with the living parents. Now, these AI systems are not isolated in our private computers. They are nowadays integrated in digital infrastructure. And you know, this global digital infrastructure started in the end of the 80s and 90s of the last century with the internet. But in the internet was only a support for human communication. Nowadays, and that means a plus sign here, a new technology came in. That was sensor technology, and that means that now the things, the objects of our everyday life are equipped with sensors. And by that, they are able to communicate with one another by codes, and even with humans, and therefore it is called the Internet of Things, not only the Internet of Humans. The Internet of Things, for example, here with our smartphones, our autocars, the robots, even aircrafts by interaction of intercommunication of codes, and sometimes also digital infrastructure of houses and cities. This is an important application for economy. This was a main topic in the last year in my country, in Germany. It is called Industry 4.0. 4.0 relates to the historical steps of the industrial revolutions. You know, it started in the beginning of the 19th century with the invention of the steam engine, and then the first period of industrialization, and then in the beginning of the 20th century with the car industry and motorization, and then in the midst of the last century, the 60s, the 70s, robotics, industrial robotics came up, especially also in the car industry, but that was at that time symbolic robotics. You remember my introducing remarks on that topic. But nowadays, and that means Industry 4.0, all these equipments and machines in a factory can be equipped by these sensors in order to realize the communication not only between humans, but also between the machines and human, and machines in order to automate the production and trade step by step. So there are a lot of examples nowadays of these digital infrastructure already existing, and they will grow together in the future. And that is metaphorically illustrated here with this picture of a brain which is spreading all over the planet Earth. And here on the left and the right, you find the catchwords for already existing digital infrastructure. I mentioned Industry 4.0, or the smart grids for optimizing energetic networks, sometimes smart cities, automobile networks in the cities supported by AI, and the huge global financial networks which could not operate nowadays without these rapid AI algorithms, the health system which should be supported by digital infrastructure. And last but not least, we are living in times of war. And war nowadays, military infrastructure would not be possible without this AI support, with automatic weapons, drones, and so on. Now, all that nowadays, these are no longer these simple neural networks with which I started. You remember only with 4 and 5 layers, the human brain with 5 layers. The networks nowadays, the real world networks in industry, they have not only hundreds of layers, they have thousands of layers. They consist of millions of neurons and billions of weights, synaptic weights. So that is illustrated here. They are represented mathematically by a network function depending on a certain input that may be the training pattern, and theta here relates to the distribution of the synaptic weights, and they are trained. They are trained here symbolically to theta star, and that means the network should approximate the target step by step. The target here, that means the task which should be realized by the system, the target function. Now, all that is the digital computing background nowadays. And now my point, which I mentioned in the beginning, with this digital technology, we are running in the next years in severe problems because of energy problems. The energy which is needed by digitalization will be in some years the biggest part of the energy, needed energy on Earth. Now, that is here explained for digital computing. You remember, we go now back to Turing and von Neumann. I started with a remark. There is a strict distinction between memory and the processor. And that is here illustrated with the classical digital UCP, and that is fine from a logical point of view, this clear distinction. But on the other side, each bit, and there are billions of them nowadays, each bit must be stored in such a memory. And then it is elaborated step by step. That means in the end, the increasing mass of data nowadays, big data, must be pressed through this bottleneck of the processor and the memory. And that is sometimes called the von Neumann bottleneck. It is like in a ketchup bottle. The ketchup here is now the information, and that must be pressed through this bottleneck, and that needs a lot of energy, and it needs a lot of time, and that is the reason of the energy consumption problem, which I mentioned before. And energy, that is one of the great challenge of human mankind. You know, with energy problem, all these other problems are connected. Our environmental problems, the climate problem because of CO2 production. And on the other side, the evolution of our brain, of the brains of animals, unbelievable efficiently from an energetical point of view. Only 20 watts are needed by our brain. 20 watt, that is the energy of a simple small lamp. Amazing for all these abilities of human brains. And now the main reason is the difference concerning the architecture. And the architecture, in the architecture of the human brain, there is no longer the distinction, strict distinction of processor on the one side and the memory on the other side. But there are networks and there are the synapses, and the synapses are able to integrate both functions, processing and memory. And there is not only one synapse in the brain, but there are billions of synapses in the human brain. So there is no danger of the bottleneck problem. And we're already using these machine learning networks. I mentioned it in machine learning, but here they are simulated on the von Neumann machines. And so there is no advantage from an energetical point of view. So the question came up, and the engagement nowadays to find hardware to realize these networks, such as the human brain, not by wetware biologically, but at least by new materials, silicon, and so on. And a first step in that direction was by an elder colleague of mine from Berkeley in the beginning of the 70s. He suggested at first theoretically the possibility of an electrotechnical unit which can integrate memory and processor. And he called it a memristor. Memristor is a combination of the words memory and resistor. And that would be, of course, a nice candidate to realize synapses in hardware. Later on, we worked out the theory. Here is one of our books. And that means the network, which we called memristic network. Because here, in an electrotechnical network, the function of the synapses is realized by such a memristor. So you have a first level. The first level is the human brain, biological brain, the neurochemical interaction of the biological neurons. And that can be, by the way, mathematically described by the Hodgkin-Huxley equations. They are named after two famous physicians, by the way, from Cambridge, Nobel Prize winners. And then on the next level, what we tried to do is an electrotechnical model of these neurochemical biological interaction by these memristive electronical networks. And that is illustrated here on the left. That is one layer. And here in the graph, you see the symbols here are the memristors realizing these synaptic interaction. And in a simplified description, it is ruled by this simple equation. The input here is voltage, and the output is current. And here, that is a linear, at first a linear parameter of this equation. And perhaps you remember your school physics, the famous Ohm's law. It is, I think, already taught at school. And Ohm's law means that voltage, that is here, voltage is equal to resistance multiplied with I, with current. And in the simple school physics and in practical today, everyday electrotechnics, R is a linear factor. And but you remember, we want to have a system with memory, and therefore R depends now on certain parameters, for example, charge or other parameters, in order to integrate the memory of our operations here. And therefore, now the resistance is called mem-ristance, the combination of memory and resistance in Ohm's law. And in the inverse case here, in this equation, this G is the conductivity, and that is also equipped now with a memory. That means depends on certain parameters, and by that it is nonlinear, by the way, and therefore it is called mem-ductance, combination of memory and conductivity. Anyway, that is a little bit of the mathematical background. These memristors mimic the weights between the neurons here. They enable energy efficient, fully parallel, analog in memory computation of vector matrix products. These G's are now matrices, and by that it bypasses the computational bottleneck, which I mentioned before in classical computing with CPUs. Now, that is nowadays already built and under construction, and in my home country, I'm engaged in these research projects. But now we are starting with the next level, and that is also very amazing and exciting. Instead of spikes of electrical signals here in the electrotechnical networks, we can consider photonic-based neuromorphic computers. That means photons, light, are now the carriers of information, and in spikes of light intensity with optical neurons. And they can operate on a nanosecond scaling instead of millisecond scaling. But it is not only the advantage of separation. These photonic networks are, from an energetical point of view, with a factor 1,000 more effective than the electronic networks. And the electronic networks are, as I explained before, very efficient with respect to the classical digital computing. This is such a photonic neuromorphic network. Here, this is a network with these input neurons X here. The H letters refers to the synaptic weights, and Y is the output. And here, these neurons are now technically realized by optoelectronic neurons, no longer by only electronic neurons, here with the resistors and the capacitor and the photonic detectors, and lambda means the wavelengths of the laser light, and so on. I will not go in these details. The synaptic interaction is now realized by light, and in this case, laser light. So we need here for transport some collections of mirrors for the light beams and the so-called Mach-Sender interferometer. I will not go here in the details. I only mentioned it because here the carriers are photons, these massless particles of light. And photons, they are quantum systems. So my next point is, my last point, that this approach of the neuromorphic computing can be connected with another famous paradigm nowadays, that is quantum computing. And in a photon as a quantum system, only the first example here, the bits 0 and 1 can be realized by different polarization states of a photon. Polarization, you know, perhaps in summer with your sunglasses, they are polarized. And here these photons are vertically and horizontally polarized, representing 0 and 1. But in a quantum system, and that is the great idea here, you have not only two alternative states, but you can consider the degrees between 0 and 1 concerning the more or less probability to be in the state 0 or to be in the state 1. And that combination, this superposition of all these states, that is nowadays called quantum bit. But by these quantum mechanical principles, you cannot only support two states, 0 and 1, but unbelievable, finitely many bits in one package. It's a so-called superposition. So in classical computer, I mentioned it already for several times, you must elaborate step by step, one after another, each bit. But here you have a whole package of perhaps millions of bits incorporated in one superposition, and you apply your computational devices to the whole package, not only to the single bits. And that means an enormous acceleration of computing. So if we would have the quantum computer, then it would be possible to solve problems which nowadays with the classical digital computing, because of the huge computational time, could not be realized in the lifetime of humans. But then it could be realized in minutes or seconds. Now, the idea is here that these neuromorphic approaches with electronic and photonic basis, they can also, should also be combined with quantum computing. That means the bit states 0 and 1 or photons can be superimposed in quantum bits so that many computing steps can be executed simultaneously. That is called quantum parallelism. And computational velocity can be improved from microseconds to nanoseconds. So photonic neuromorphic computing with quantum computing, that is, so to say, my research vision. In the end, can lead to a kind of brain-oriented computing system with light. I like to call it sometimes, it is an artificial brain of light. And from the sustainability point of view, it would reduce energy consumption for sustainable AI. Now, in the end, let me consider and summarize the future challenges of all these approaches. There are two main tendencies in technology which I highlighted during my talk. There is first the tendency, what is sometimes called more Moore technology. More Moore is based on Moore's law. Perhaps you remember Moore's law says that with decreasing size of the chips, the computational power is increasing. And that was fine for a long time, but nowadays Moore's law run into limitations of miniaturization within nano and atomic scaling, because then a new physics started. And traditional semiconductor technology must be overcome by quantum computing. That is the red arrow. Now the blue arrow, I call it more than Moore technology. And that means the neuromorphic tendency, more brain-oriented, analog computing, sensors, biochips, for example, are for our communication with our environment. I mentioned already the robots. So neuromorphic computing, and then in the end to integrate both tendency, which is here illustrated in the diagram with this diagonal arrow in violet. Now, a short remark, in what state are we concerning a quantum computer? Concerning quantum computers, we distinguish 3 generations. The first generation, that was already in the late 70s and 80s of the last century. That is quantum technology, which in those years were already realized, for example, by the lasers. The lasers integrated in all kind of technical equipment. Now, the second generation means first prototypes of quantum computers with rather few quantum bits, and these prototypes are only reduced to solving certain specialized tasks. The third generation would mean the universal quantum computer, such as you remember Turing with the digital computer and the universal Turing machine, and that would means we have so much quantum bits in order to realize a general purpose quantum computer which can be applied to any kind of task like our digital computers nowadays. Actually, we are now technologically speaking in a period between the second and the third generation. That is sometimes called NISQ in the abbreviation, and NISQ, that means noisy, and intermediate scale noisy, because the number of quantum bits is not sufficient to correct the failures, such as in a classical digital computer, and intermediate scale because the number of qubits is sufficient for the proof of supremacy of some computers for specialized tasks, but insufficient for a universal quantum computer. Now, all that does not mean that in the end we will not only have quantum computers or neuromorphic computers. No, all these different approaches have certain advantages and disadvantages. They are specialized for several tasks, and so the future will be hybrid AI with symbolic AI, machine learning, neuromorphic AI, quantum computing, which should be integrated in hybrid AI to accelerate our problem solving with increasing complexity of our civilization. And now in the end, a remark to the European AI, what we need in Europe, that is standardization and certification, because on the one side, the national diversity in Europe may be an advantage from a cultural point of view, but in technology, the diversity makes it sometimes complicated. What we need with respect to the worldwide competition, and there are strong competitors in the world, in Asia, in America, and so on, we need a concentration in Europe of our innovation power for a sustainable and responsible innovation, which I explained before. And that is my last foley, worldwide innovation competition. That is the future of Europe, and I hope that in the near future we will be supported also by your academy in the European competition in the world, and that is a special wish of mine on the day today of your National Day of Independence. I thank you for your attention.